Starting this morning, we're going to be going through a set of hands-on exercises to help you build up success of familiarity with AnyLogic and to expose you in a more systematic fashion to a number of the features, the elements of the modeling vocabulary of AnyLogic. We're going to be interspersing that with some additional talks. For example, Andre is going to be talking tomorrow, giving a public presentation, and we're hoping to lean fairly heavily on the existence of some of that material to which I referred you earlier with that URL, which is available online for more in-depth training. Normally when I do a boot camp, it's a 5-day exercise plus a 6th day for intensive project consultation between experienced modelers on the one hand and participants. Trying to compress that into 3 days is a tall order. Hence, we're going to be going a little bit lighter on the material, still providing systematic exposure, but going a bit lighter, and offering recourse to the online presentations for early intensive coverage. You'll also find that the slides that I've provided include quite a bit of additional material that I won't actually be covering directly in my comments, but of course I'm glad to it's material on which I'm glad to answer questions. Okay. So we, I guess I should mention, we did secure feedback from participants as requested with respect to what they're hoping to get out of the session. I've not yet enjoyed the opportunity of familiarizing myself with those comments, but hope to do so perhaps during the break or at some other point where I'm not up here in front of you. I just haven't had time to go through it. Just received it. So we'll see if we can hit on those points, and we'll see if we can use this sort of lighter coverage to make sure there's lots of time for answering questions and discussion of the more conceptually challenging or textured issues that will be covered, because there's a lot of training that can be done, but in terms of balance of time, while we do a good amount of training, I want to be sure that we cover a lot of conceptually challenging issues, so it's not merely, teaching you how to manipulate the interface, but also helping you think through some of the issues. Okay, so we're going to start with one example, but before I do that, are there any questions that I could address right now? Questions? Okay. I'd like you to all fire up your AnyLogics. Participants, start your AnyLogics. We're going to be keeping them up pretty much for the next 3 days, so you might as well just maintain it. The other thing I'd like you to have ready access to is the set of examples that were provided. So there's exercises, but then there's a set of example models. We're going to be building a fair number of those models up together. Things like a hierarchical model of multiple levels. Things like a model of network-based context, mobility models. But I found that it's much more reliable if students can go open a model if their previously built one isn't working quite properly. So for most of the models we'll be building up, there's going to be a corresponding example that you can go open and try to figure out what might have gone wrong with your example, or to build atop that, as we'll often do. Okay? We'll be building up structure that will then be used further, and if your structure is not as solid as you'd like, you could load in the example model and go from there. Okay? So be sure to have those handy. For this initial example, however, we're going to be using a built-in model. What I'd like to do is expose students. So thus far, what you folks have seen is predominantly glimpses of models already built by somebody else. And what we're going to be doing is getting you your first exposure and modifying a model first without all the overhead of building it up. And then we'll go through exercises building up models. Okay. This first lesson will give you some exposure to modifying things in the AnyLogic interface, running scenarios yourself, thinking through some of the issues. So it will expose you to the interface. It will also provide a what I consider a pretty interesting example of emergence, of spatial temporal emergence. So I'd like you to go and open up an AnyLogic example model. To do that, you go to the Help menu here, and you'll indicate example models. And as I will try to do for the next few days, I will follow along with this. So let me just close this example I was working with last night, and I'll try to go do this same thing. So help example models, and this being Eclipse, you'll see the appropriate window appear at different places depending on your current settings. Right now it's here at the bottom of the screen. As I had indicated, we could kind of, oh, look at that. We don't want that. So help example models. Here we go. And we're going to scroll down and open up SIR agent base. So you'll select, to get to that, you'll select how-to models, and you can scroll down on the right to select SIR agent base. So here we are, we're selecting how-to, and over here on the right there'll be an admirable wealth of different models. And if you scroll down, there'll be the SIR agent based. Okay, we're going to sort of return to a familiar, what I hope will be a familiar friend to you. Perhaps for some it will become a familiar enemy. But a depiction of infection spread. So this model simulates the spread of infectious disease in a regular space. By regular space, I mean there's no craggy sort of irregularities, craggy sort of areas where the infection has a harder time moving, or there's no discontinuities associated with physical barriers like rivers or something like that. This is a uniform space with uniform characteristics arranged in a grid pattern, with connectivity just in 4 directions, north, south, east, west, so the 4 cardinal directions. And the simulation will start with a single index infective case, which is located actually at a random point in space. And there's going to be a natural history of infection. So if we go and we look at this, you'll notice the model is composed of several pieces. Main, this class whose icon is similar to Da Vinci's measure of man, sort of a person with outstretched arms and legs. This is an indication of an agent class. And then we're going to have 2 scenarios or experiments, which each of which will describe a simulation with particular parameter values. Okay. So if we double click on person, we'll see that we have this familiar depiction of staging the natural history of an infection. People are susceptible until they become infectious through contact with others. While in an infectious state, they actually can infect others through successive contact, and at some point they recover. Okay. Now we'll go in and look at the logic behind this further, but that's the sort of high-level view of what's going on. The way this infection will spread, it will spread from a person to neighbors in only 4 directions, north, south, east, and west. So it's localized spread. They're not spreading to someone way across space. You require physical proximity for spreading. So if you double-click on person, you can see the state transition diagram. Double-clicking on it will open up this window in the canvas. And I'd like you to run the model by right-clicking on an experiment. Mine actually has 2 experiments here, but I think that's because I've modified it recently. So if you right-click, you probably have 1 experiment called simulation main. Is that right? Okay. The main indicates that it's a simulation based on the so-called main class, the class that's named main here. You can have simulations based on alternative model structures, for example. Okay, so when we ran that, how did I run that? Well, there's several ways. Let us count the ways. we can right-click on it and do Run, or we can use this button up here and choose it. There's probably, yes, there's an additional way I'm forgetting in terms of Model, Run. So there's a variety of ways. I enjoy right-clicking, but right-clicking is not everyone's preference. You should know there's other ways. Okay, so if we right-click on it, up will come an introductory screen. Now these introductory screens are right now just serving as a kind of pass-through, but you can use them to set a variety of options in AnyLogic. For example, you'll see this little golden triangle. That's not a geographic description, but a visual one. And in the golden triangle, by clicking on it, you can ask AnyLogic, for example, to display the model time here. And we'll actually be seeking to do that. Alternatively, you can set it to display other information of interest, information concerning the sort of degree of detail it provides on a variety of different topics, including performance and amount of memory consumed, etc. Okay, so to simulate this model, by the way, this indicates that it can run at the fastest speed possible. To simulate it, we just press the button, and up will pop something. Sometimes we have quite elaborate settings additionally on a model-specific basis that we'll set up. And one of the most powerful things about AnyLogic is the ease with which we can set up the user interface to our liking. Okay, so I've just clicked on this, and what we see is a depiction of an underlying process. You'll notice that susceptibles are indicated in yellow, red denotes infectives, and this gray denotes people have recovered. Can anyone, I'm going to pause this for a second, using this button, the button up there for pausing. Can anyone interpret for me what's going on here? What are we seeing and why? So those of you who are running it should be seeing action proceeding similar to what I have here. Why are we seeing this? Okay. That's correct. That's correct. So why is it moving out in this sort of circular pattern? Did we put that circular pattern in the model? Where did that circular pattern come from? It is spatial. This is space. Each person is transmitting to their neighbors. And a given infective will transmit to people on the north, south, east, to west, the left, up, down, and right. So why are we seeing this sort of circular pattern? Where's that coming from? Exactly, exactly. So it's an emergent property. It's emergent spatial property or spatiotemporal property. We see this sort of enlarging ring. Why are all the infectives concentrated out here on the edge? Okay, if they're, so there's a propagation of infection out. Each infective may infect someone on this periphery, and over time, that person may infect others, but will inevitably recover. So these people in the interior, the infections spread through there. It's like a wildfire in the outback. It spreads from a central point, and all the actions on the periphery. In this region, the fire's already spread. There's no fire to be had anymore. It's charred all the fuel for it. And the infection is spreading out. The fuel is available to the fire on the periphery, and we have a successive enlargement of that periphery over time as it consumes more and more of the surrounding susceptibles. Now, we could run this thing through to completion, and it'll propagate out. And I'd actually like you to keep track of the time. So I selected, using that golden triangle, I indicated I wanted to have the time. And I'm going to time it till it gets to the top area of the screen there. Okay. So this one actually started very low down, and it's going to take a little bit of time. get there yet. You'll notice when it reaches the border, we're just assumed that there's nothing to be infected outside the border, so it essentially it has nowhere to go and just reaches the border. It doesn't wrap around in any way, although that is possible to achieve. Okay, so we're just about at the edge here, and it's taken roughly time 300 from the start point. So what we saw there was an emergent pattern. It was a spatial temporal pattern. So it involved change over time in number of infectives, but also change in the spatial location. What I'd like to go through is a set of exercises where we modify this model now. Okay, so we just ran this out to the edge. So I timed it, and it took about time 300. And we're going to compare this to a situation with other assumptions regarding the progression of infection. We're going to tweak some model parameters and, in fact, modify the structure of the model. Now, before that, I want to communicate one important principle. You'll notice if you click on the simulation, there's a whole set of options we can set. One of them is the fact that we are using a fixed seed here. Now, for those who are not don't have a long computational background, that terminology seed may seem interested. Indeed, this model has little agricultural or horticultural tie-ins. The notion of the seed here is a random number seed, and basically this is a stochastic model, so there's randomness in it. And in order to get that randomness started, we need to give a seed, and it's a somewhat chaotic process in the sense that giving seeds very close by each other can still lead to highly divergent sort of behavior. If we give it the same seed every time, we'll get the exact same sequence of stochastics, assuming we haven't modified model structure of parameters. So we're having this fixed seed, and we're going to make use of that in successive runs. Okay, so what I'd like to do now is to stop that simulation, and we're going to actually go modify this model. Okay, so I'd like you to copy. We're going to create a new experiment. Okay, this is the most modest modification we can create. We're defining a new scenario. Okay, so if you right-click, yes. Oh, okay. Okay, if you go help, how to, so help example models, and you go under how. Yes. Okay, so here you go help example models, go to how-to models, okay, and then you scroll down and there'll be an SIR agent based. See that? You'll also find that if you have reference to my slides, I show in detail exactly where it is in the menu and so on. Incidentally, this is one area where consistency between AnyLogic versions would be valued. So it would be great if there were a common way of navigating that would last between AnyLogic even minor versions, but I'm sure there's reasons for shuffling things around. So what we're going to do here, once this model is opened, and you folks can start up right away who have just opened it for the first time, what you could do is to right-click on this guy here and do copy. Okay, so we've right-clicked on the experiment. You do copy, and then right-click on the name of the project as a whole, and do paste. Okay, so all we've done is we've created a copy of this experiment, and we're going to then modify the assumption. Okay, so in short, we clicked on copy here. We did copy. And then we clicked on the experiment as a whole and did paste. Essentially, we're just creating another copy of the original experiment. So where you see that experiment name, what I'd like to do is to change that name to slow recovery. Okay. Now, to avoid confusing you, I'm going to delete the one I already have with that name. So in other words, right-click, do copy, right-click up here, and do paste. Again, for anyone who's falling behind, you can look at the slides and you'll see exactly what I'm doing in my slides, okay? Okay. It's a lecture called Emergence and Software Introduction. Okay. Other question? I'm copying the experiment. So there's an experiment called simulation : main. It's called simulation, and you do you can do copy through by right clicking, or you can do copy through edit copy, and then or you can do it through a button on the top sometimes, and then you can right click here or do paste. Okay. So this is just kind of learning how to use the AnyLogic interface so we can create an experiment without redefining everything. Okay, we just want to modify one thing, so I'm just making a copy of this one, then we're going to tweak it. Other questions? Okay, so for this new experiment, I'm going to name it slow recovery. You notice, where do we do this naming? Well, we do it down in this properties panel. Okay, so there's a properties panel down here to the right, and you'll name it slow recovery in the name field. This will copy just about everything. The one exception is it doesn't copy the name of the model in which it's based. So over here, you'll notice there's this thing, main active object class. You're going to have to select main there. Okay. So in short, ladies and gentlemen, we've done just two things. We've copied and pasted. We've changed the name to slow recovery, and then this field here, we've changed it to depend on main. It needs to know you're depending on main. Again, this is all in the slides, so you should be able to see that. Okay, any questions about this? Okay, so here we're telling it, okay, we're going to be using this model, whose main class is associated with main. That's the class that's going to define the global environment of the model. Okay, having made those modifications, we're going to make one more modification. We're going to go down to the parameters tab, which tells us the assumptions we're going to bring to bear for this scenario. It tells what we want to assume about model parameters, okay? Now, these are all numbers, but as I said, AnyLogic has huge flexibility in terms of the nature of the parameters. Right now, what we're going to change is the average illness duration from 15 to 50, to 50. Okay? So the original one, average illness duration is 15. This is in the parameters tab here in the properties window for this simulation experiment. So we selected that, hence its properties show, and then we're going to select parameters, and we're going to set the average illness duration to 50. Okay? Okay. Any questions on that? Okay. So now what we're going to do is to run the model. What do you think? We've just changed the duration of time that it takes someone to recover. Let's go see where this matters. Where would I look? Where in this model would I look if I wanted to find where the average illness duration is used? Where in this model would that be referred to? Anyone? Sorry? Yeah, which transition? Recovery transition. So let's go look at the recovery transition. Let's see why this parameter matters. Let's see how the model works, okay? So we go to this recovery transition, and we see a rate of 1 over the average illness duration. This get main is referring to the fact that that parameter is something that's kept in the main class. We'll be getting to that, what that means. But here, the rate of this is 1 average, the average illness duration. Ladies and gentlemen, this is, when we say rate here, and I'll go into this in more detail in our introduction to state charts, this is a hazard. This is a chance per unit time of recovering. The assumption being that if you're in this infectious state, you have a certain chance of recovering for each successive unit of time, your day, no matter how long you've been in that state. So maybe you're in that state for 15 days on average, and so you have a chance of 1 over 15 chance per day of recovering. And it turns out all the mathematics works out, and if you look at my lecture slides online, you'll find a mathematical derivation as to why, in fact, if you have a mean time in that state of average illness duration, that associated hazard of leaving the state is 1 over it. Okay? So if you're there for an average of 2 days in that state, you have a chance of 50% per day of leaving. Okay? so here we're in this infectious state for an average of average illness duration. The bigger this is, the less chance on a per day basis we're going to leave it. Okay? This is just a relationship we commonly see in modeling. It's associated with a first order delay. It's associated with an exponential residence time. For those for whom that's meaningful, it's a common modeling construct. Okay, so we're going to now run this new model, this new scenario that we've defined. How will what we see be different? Does anyone want to posit? Visually speaking, what will we see differently? Just looking for the phenomenology of it. There'll be more reds. And it'll be wider. Very good. So these are two different descriptions, interestingly, at different levels of abstraction. More reds is about the total number over the entire space. It abstracts away from the spatial configuration. Thicker edge is a spatial description, which has to do with the fact that here we have not just reference modes over time, we've sort of patterning over space as well. So let's go run this model. So how did I do that? I right-clicked and I did run. So I right-clicked and did run, or again I could do model run, or I could do it with the button up top. And so here we're running this. This is our slow recovery scenario, and I forgot to set the time. So let me go down while it's actually running and select model time. You should feel comfortable with that. And as we'll see, there's a bunch of powerful things we can do using these menus. For example, we can drill down and see what's going on with particular people at a time, who's in what state at different times, and we'll be going into that in more detail later. But for now, I just tweaked it so we could see the time here. Okay, so this thing is running quite quickly. You'll notice it's actually running slower. I mean, in terms of the amount of time it takes to increment a given unit of time here, it's actually slower. That's because more is going on. In particular, there's more messages being sent. AnyLogic depends underneath the covers on what's called an event schedule. And that event scheduler has more work to do when there's more things to do or more things happening. Some of those things happening will be one person sends a message to another, for example. Another will be a state chart transition that has to take place. Here we have a lot more messages being sent because there's a lot more infectives. They're sending all these messages. This one in here, this red one right in the center, that may be in a different place, that's sending messages to the ones around it saying, hey, you're exposed, but it ain't mattering because there's no one around it who's susceptible. This is running. It's running really slowly. Well, we could run this out, and I think as it's running, I'll go and point out a little bit of an additional element of how that works. Let's go up to the infection transition. You folks don't have to follow this on yours if you want to just keep that image up on the screen. You notice this one is transition. It's triggered by a message. So while a person's in an infective state, they are sending messages to their neighbors in space. To a neighbor from either north, south, east, or west. And then if those neighbors are in a susceptible state and they receive that message, they're going to get infected. If they're in some other state, for example, if they're recovered or already infected, they just ignore the message. It doesn't mean anything to them. But a lot of messages are being sent here. Okay, so this thing is running through here. Is anyone's finished now? Anyone's finished? Okay. How long did it take? Do you have a time shown? Okay. Okay. So, is that what if thinking about someone recovering slower, how do you think that would affect the speed with which the infection propagates? If people recover slower, does anyone want to hazard a guess as to how that might affect how quickly an infection spreads through a population, sweeps through a population? Well, if they're infected for longer, are they going to be infecting over the course of their illness more or fewer people? Typically more, and therefore it's going to enhance the total number infected, perhaps, but its impact actually on the spread of the timing of infection is also there as well. So an infection is going to go up. The number of the rate at which it rises will be affected by that as well. Here, what we see is that the infection timing doesn't change much. Why not? We have a lot more people infected here. We would think that they're infecting more people. Why is it that it's not spreading out? Yes, sure. Sorry. Okay. Okay. So comment more on that. If we're only contacting our local neighbors, our immediate neighbors, then we're going to have the same speed of infection. Okay. So in other words, even though there's more infectives, a lot of them are in this kind of thick band that was alluded to here. These folks here aren't infecting more people over the course of their illness. They only have kicks at the can to infect the people next to them, not to infect others, at arbitrary positions in the space. There's no random mixing going on, as is common and with the assumptions of models. Instead, people are limited how many people they can infect. They can infect at most 4 people, right? Even if they stay infected for a very long period of time, they're limited in how many people they can infect. So here we have more infectives. Here we have a thicker band, but it doesn't translate into faster speed of propagation. It's not true that the longer they're infected, the more people they'll infect over the course of their illness. That's a very small effect. Let's put it that way. It's a very, very small effect. It is possible. It matters slightly. But here we can see it reaches the edge in pretty much the same time. Because spatially, the influence, the ability to sort of infect others is limited. People are trapped in a matrix of grid cells, and they're not able to infect additional people around them. Okay, so we saw something like this, which has a quite thick periphery. So what we've done is we've defined a new scenario, and we've modified the assumptions as encoded by parameters. Let's go modify the model structurally. So what we're going to do is add a transition, okay? We're actually going to modify not the parameters here of a particular scenario, not the sort of specifics of what we're going to assume about this model when it runs. Instead, what we're going to do is modify what is going on, sort of how it works, okay? Not merely some components of the degree to which different transitions occur, etc. So to add a transition, we're going to go over to this thing called palette on the right. And in case you can't see it, you'll notice in the view menu, you can enable or disable windows. So for example, I could go to view, and you may notice palette is not shown. You can right click on it, and it will spring into being at some part of your window. So if you go to the palette window, you should be able to go down to the state chart area, and you'll notice there's a thing called transition there. I would like you to drag a transition from the palette and to the recovered state. So you're gonna take a transition and you're gonna drag it so that it comes from recovered. You'll notice it has an arrow at its front end. You want that arrow not going into recovered but coming out of. We're gonna add a transition, ladies and gentlemen, for the waning of immunity. Okay, immunity is not going to be permanent. It's going to be temporary, and so we're going to drag that in. You should see a green dot appear there when you do that. I'm going to just do this again for those who can follow it. I'm going to drag from transition here so that it comes out of the recovered state, and then what I'm going to do is to go drag the other end to the susceptible state. So waning of immunity, people will wane from a recovered state to a susceptible state, which will put them in danger now of being infected again. Now, as you can see, the aesthetics of this transition are limited. It goes right over another state here. So I'm going to double click on the transition, which gives me a little handle which I can use to sort of drag out and position it outwards. the semantics, the logic is not changed by that, but it appears in a more salutary fashion. So I've just added this transition. I dragged it so it's coming out of recovered, going into susceptible, and then I double-clicked on it to get this handle and dragged it out. Okay. Now we're going to now give some properties to this transition. The first thing is I'd like you to type its name, waning immunity. Okay. So waning immunity. You could call it loss of immunity if you saw fit or what have you. Okay. So waning immunity here. And as a general good practice, it's good to show the name so that people can use the name to have an understanding of what that transition might represent. So I'm clicking this button that says show name. Why am I seeing this property for this transition? Well, it's because that's the one selected. If I click on it, then I see these properties. So I clicked show name, and now it's showing this name, and I could drag it around as I see fit. Okay. So that's one thing I want to change, its name to waning immunity. This element is actually the name of an underlying Java variable, and as such, you need to adhere to the strictures of Java. Now that sounds unpleasant, but basically you need to make it a single word. You can't put punctuation like commas or dashes. Basically, you're safe if you stick to alphanumerics. You don't want to put a number in the front, but you can put a number later if you want to. And generally, I think it's a good practice to use what's called camel case. So when you have several words in a line, either separate them with underbars to separate them, or capitalize the name of each successive word. And that allows you to kind of parse out the different words that are a component of this. Okay, so this is waning immunity, I with a capital I. Okay, so waning immunity, all one word. Okay, and I'd like you to set the semantics of this to be something different. We already saw a rate transition, which establishes a constant hazard, leads to exponentially distributed residence time. You have the same kick of the can for leaving a state every successive time unit, so no matter how long you've been in the state. We, ladies and gentlemen, are going to put in something different. It'll be a timeout transition. This is in contrast to a rate transition with a fixed hazard, which is memoryless. It doesn't matter how long you've been there for your chance. This is very memory full. You are going to leave exactly a certain unit of time after coming in, and I'm going to make it 100. Okay, so exactly 100 time units after you transition into recovered, you're going to leave with the waning immunity transition. This is just illustrating another form of transition. We'll see several more of them later when we systematically cover these. Okay. Okay. So we have this waning immunity transition. That's good. So we're going to run this model now. We have modified, ladies and gentlemen, the structure of this model. What do you expect to see different? We've run the model with a fast recovery and a slow recovery, a default recovery time and a slow recovery previously. Now we've modified the structure of the model. How will what we see differ from what we previously saw? Okay, you'll have susceptibles appear again. That's very, very important. Where will they appear? In the gray area. Okay. Yeah. Okay, good. The ones who have been recovered for the longest, so it'll perhaps start way in that gray area, maybe where the infection originates. You'll start to see new individuals come in. Okay, so let's give this a shot. So I'd like you to run the, not the slow recovery, but the original scenario. So you'll notice now we've modified the model. So when we run these scenarios, they're running it with the new model. If we want to have a whole new version of our model, we could actually create a new main class which has, a new main class which has this newer model in it and leave the old main class the same. Or you could save away versions of your model. Okay, so we're going to run this thing. This is the original scenario, and we're running it. Okay, so here we have this thing starting up. Do you see anything different yet? Why or why not? I'm going to turn on the time here. Does it look different? Oh, good eye, good eye. Okay, yeah, good processor. Okay, so why are we seeing this? What are we seeing here? Okay. Okay, so we see successive waves of infection. A first wave further out, another wave which was preceded by the emergence of some susceptibles, now getting infected from, who are they getting infected by? Those few that stay behind long enough that they're still around to be infected. Let's keep on running this thing. So if I'm running this, what do you expect to see over the next few minutes as this sort of proceeds outwards? Multiple waves of infection. In fact, we even see sort of sub areas of infection that form locally. Where do these guys come from? Sort of why are there these kind of blotches there? Note this red guy there. The seat, a blotch. So they're coming from what Bjorn referred to earlier. They're coming from the sort of they nucleate around these sort of individual remaining infectives. So here we have yet another wave emerging, and from the preceding wave, there's still some individuals around who remain infective, and so we have these successive waves of infection. Okay, so that's a quite distinctive phenomenology. These waves, are they? Where are the waves here? Where's the wave? Where is it? Is it here? Where's the wave? Is it here? Where is that wave? Okay, it's an emergent property. It comes from. Does it come from this? Yeah, it's influenced by that. Does it come from this? Yeah, it's influenced by that. Does it come from this? Yeah, if we recovered really quickly, we might not get those successive waves, right? So it's an emergent property that emerges from all of them. It doesn't appreciably affect the timing, but it does lead to a very different phenomenology. Now, ladies and gentlemen, what would this look like if we were just looking at the aggregate number infected over time? We just totaled up over the entire space the number that are infected. What would this translate to? We're seeing it spatio-temporally, but if we were just dealing with aggregates, if we were just dealing with counts of infectives, what would that look like? Anyone? Sorry? Replaced by ones. Right, there's going to be some yes. Yes, exactly. So at the cost of being unscripted, as I am wont, I think I'm going to click on main here, and we'll just go see. So let's go up to where we see, if we double click on main, you'll see that we can go up and click, and this is where the counts are current. In case you folks didn't notice it, up at the top of that, it was counting the number infective at any one point. And if we go click on this item, we'll see that it has a, it's actually displaying a value here, which is, oops, sorry, I meant to click on this here. Which is displaying a number of the count of infectives at any one point. And you'll notice it's kept track of in a variable called n infectious. Well, we could go create a little chart that shows that. So this will be a glimpse of sort of AnyLogic's chart. So if we scroll down here, we're again in main, we scroll down, let's go see how we can add in charts. So if we go down to analysis, and this window is obscuring my view. Let me just deal with that distraction. So you can see the full view here. If we go down to analysis here, we can actually note that there's a thing called a time plot. We could drag this in, and this will create a user interface element which will display a plot of some variable over time. And there's lots of options for this. I'm going to enlarge it here, and enlarge it vertically and horizontally. And then what I'm going to do, so I dragged in from time plot, which is down here in analysis. And then what I'd like to do is go up to the general property of it, and you'll notice it just says plot. I will say, you know, plot infectious. The plot or plot count infectious is probably a better term. Choosing names, ladies and gentlemen, is important. I give the better part of a full lecture in my software engineering class in choosing careful names. Names are one of the best ways you can communicate to somebody else the purpose of things in your model, and to communicate to yourself in the future when you come back to a model you haven't worked with for a while. They communicate what things do. So they're not throwaway things. They're things that are important. So here we'll call it plot count infectious, and we can add a data item, and that will tell, okay, we would like it to plot a certain value. In this case, it'll be a variable called n-infectious, okay? Java is case sensitive. It's not going to be happy if you change the case to something. It won't recognize, it's kind of dumb in that sense. It won't recognize that n-infectious with a lowercase I is the same as n-infectious with a capital I. You can argue about whether that's desirable or not, but you want to be careful. So this is lowercase n. That denotes normally a count in the conventions of my kind, and then it's capital I infectious. Okay, so this is a count of infectives. Where did I get that thing from? Well, I just took advantage of the fact that it's already used. Okay, it's something we already saw used. When I looked up here, I saw it was depending on a variable called n-infectious, so I'm going to use it. Later, we'll see how we can compute it ourselves or compute custom things. So how did I get this? I named this thing plot count infectious. I did plus to add a data item, and then I just filled in n-infectious here. Okay? Any questions on that? Question? Okay, so ladies and gentlemen, let us compute. So let's run this thing. So over in simulation, we're gonna run simulation, and we're gonna go see what this looks like in terms of aggregate graph. Now, where's the plot? Anyone see the plot? Sorry? Exactly. So it's actually located below this area here. Okay. And in this case, this is not set up to, unfortunately, to scroll around. So I'm going to have to probably adjust. Exactly. So down here, and what is it? Presentation? It's window. Okay. Thank you. Enable panning. That's the one. Okay. Thank you. So sort of scrolling it around by or moving it around by the right button is enable. You do it through this enable panning. So I went to the experiment window, clicked on enable panning, and I'm going to do this now. And we can actually set the size of the window too, but for speed, I'm just going to do this. So if we go, we could scroll down here, and what we see is a number of infective. And actually, this curve here, which rises proportionately to, for those who are interested in these things, the exponent of the basic reproductive number minus 1 divided by the mean intergenerational time. It actually rises initially in a fairly exponential way, and now we see these successive waves of infection. And just as was said earlier, they don't seem to have a really pronounced impact on waves in this aggregate quantities. In short, these waves that are recognized here don't appear immediately in terms of the aggregate statistics on the system. Now, if we run this out over time, we'll find that the count of infectives reaches some peak, and then it will will start to more oscillate, although it won't be in a terrifically pronounced way. So it's kind of plateaued here. And we're seeing some slight oscillations here with the outermost wave, I think approaching the edge of things. Okay, yeah, it's not quite up there. In any event, what this gives us is a quite different picture. The aggregate statistics don't directly sort of bear out the richness of what's going on at a spatial temporal level. They capture some components, for example, the fact that early on it grew very, very quickly, and there's some fluctuations that you can see associated with these aggregate statistics. But the full nature of the waves, the fact that they're recurrent, and the thickness of the sort of wave fronts is not entirely obvious. But what we see here is a fairly textured case, and a case where the extra level of visualization of what's going on spatially is important. Also, the fact that we're spreading in a limited style of space, really in a limited area of space and only to neighbors, gets in the way of classic assumptions we use in mathematical epidemiology concerning random mixing, which would assume people can be in contact across the space, etc. Okay, so here we reached a peak, and we're coming down again, and we're going to have some oscillations sort of in place subsequently. Okay, so here we've just added some output from this model. There's lots more we could, and you could let your imagination go wild. Certainly if people recovered very quickly, the second waves wouldn't be occurring in that way. We would probably just have a single wave. For example, we could do copy again and paste here, and we'd end up with just a single wave if we set the recovery time to be quick enough. So I'm just going to have fast recovery, and we'll run that. Okay. So what we've seen here is a beginning model. We've modified the model parameter assumptions. We've modified the model structurally. And we've seen how we can actually end, excuse me, for the fast recovery I need to set its main class to be main. Okay, now I can go down to parameters. So average illness duration, if I change that to 5, for example, and we run this, we'll probably see a much different picture yet. And we've seen how we can add UI elements to the model here. In fact, with a recovery duration of 5, I don't see anything. Can anyone say why that is? Why don't I see any infection spread if I have a recovery duration of 5? Well, for those who have encountered it, it means the basic reproductive number is less than 1. And in general, each person infects less than 1 person before they recover. And therefore, we see a situation where the infection just dies out. They may infect 1 person before that person recovers, but it peters out very quickly. Here's a case with an infection time, recovery time of 8, which is enough to get it started, but not so high that we have a lot of individuals sticking around. So what do you think we'll see in this case? Will we see successive waves? Sorry? No. We'll actually get more or less total recovery of individuals. What would the aggregate graph look like? How will that be different? Yeah. So it actually reached a peak, and now it's going down. It's actually a fairly small number of infectives. Oh, look at that! What happened? happened there? Well, there was one person remaining infective after a long period, and it ended up seeding it. Okay, so this thing is going to cycle until it's not lucky enough to hit another infective, or unlucky enough as you see fit, and at that point it will be all susceptible, and that's it. So a little bit unpredictable about how this goes based on the vagaries of the stochastics involved. Now it's back up to the climbing, but you know, unless there's one residual infective, it's unlikely to go again. So here the stochastics can be actually very pronounced based on the vagaries of when people recover. So the question is, will that guy? Oh, it didn't survive, so we'll get an entirely susceptible, I think. Oh, nope, there we go. Okay, so this is your first example of a model. You've modified it, you've added scenarios, you've modified the structure, and we've seen how we can add UI elements. Any questions on this model? Huh? Okay. We have a bit additional time here. My thought would be, Jeff, to actually have them build up a little pre-canned model that I have here. Is that okay with you? Or would you prefer to switch to something different? Okay, sure. Okay. Very good. So this was sort of brief introduction here. I think what I'll do is